So now in this video, we have a PNP bipolar junction transistor right there, the 2N3906. Earlier video, we used the 2N3904 and NPN bipolar junction transistor to make this circuit, but since they're opposite chemistry, this is PNP, that means all the components are going to be headed towards the opposite supply from what they were in the earlier video. Whatever circuit you can make with an NPN bipolar junction transistor, you can also make with a PNP. You just have to remember polarities are opposite. Hopefully that makes sense. So compare, equal circuits that are NPN and PNP, and it'll make more sense. So we're making the same circuit here, and we will zoom in. You could see the physical component there, or circuit there. We'll come back to that. But ultimately, we got the PNP bipolar junction transistor here, wired as an emitter follower. So you can see the load is between the emitter and a supply voltage. In this case, the positive supply, because it's PNP right there. So the load follows the emitter. You can think of electron flow with the PNP bipolar junction transistor. And so when you have a trickle of current going to emitter to baser, it's going to allow many times the current to go from emitter to ground. Again, we're talking conventional current at this point. And that's just an old way that they didn't know which way current or electrons or whatever were flowing, so they just kind of assumed positive to negative, and that's kind of how we look at circuits today. So usually you'll see the arrows pointing from positive to negative to let you know the correct current flow. So in any case, what we are going to do is set a voltage at the base right there. So we're going to use a zener diode, 5.6 volt zener diode. When you use them reverse bias, so this is the way that you force them to pass current in the direction you don't normally pass current through diodes, but zener diodes are specially made to pass current at their zener voltage. Once the voltage gets that high, then they'll start conducting current, and they conduct current, freely at that point for the most part. So they'll maintain about that voltage across them, and then so we got to limit current. But in any case, we are going to be subtracting now. So if we have 7 volts there, we're going to subtract about 5.6 volts over to this point. So that'll leave about 1.4 volts across the resistor right there. And in any case, we are subtracting that voltage there. Ultimately, that means that we got about 0.6 volt difference between these 2 points. Again, it will want to pass current, but only when this voltage is high enough to do so. So it's got to be about 0.6 volts higher. So remember, we're subtracting that voltage there. This is a little bit higher. So we'll have a higher voltage there than we do there. Ultimately, it'll be a 0.6 volt difference. And so we'll maintain about 5 volts across there. Now this 10K resistor you may not need at all. It may be totally pointless, but sometimes if you have a tricky load, you have a bunch of like LEDs or something that drop voltages in a weird way, then the emitter might kind of lose track where the positive supply voltage is in that case. That resistor there always gives you like a little current coming that way to let you know, yep, that's definitely 7 or 15 volts up there. So that's the best sense I can make of it. I've had circuits that the load threw off the voltage until I put the 10K resistor there. Then it maintained the proper voltage across there. So that's really about it. If we use a lower value resistor, we would probably get a better zener voltage, a more solid, especially since we're using an NPN bipolar junction transistor. But 10K seems to work okay, so I'm using that until I have to go lower. So we can go up to 15 volts. We would not be able to if we were just using a 1K. I don't think. Maybe we could, but that'd really be pushing it. So we can go 15, maybe even 20, I don't know. But definitely 15 volts as long as we have this 10K resistor there. Remember, we're putting about 5 volts across the load, so the transistor handles the rest. So if we got 5 volts across the load, which the transistor sets in this circuit, and we're using a 10 volt supply, then we'll have 10 volts across the transistor. So you have to keep that in mind when you are wondering about the power needs of the transistor. So the load is going to set the current in this case right there. It'll be that current times 10 volts across the transistor if you're using 15 volts, because that dropped 5, as I said before. So in any case, that's enough rambling. Let's look over here. There you can see our 5.6 volt zener diode black band there, right there to the positive supply, and our 10K resistor there. They're coming to the middle pin of the PNP bipolar junction transistor. So since this is a 2N transistor, I think this is always the case, but I could be wrong. I always check the data sheet, but 2N3906. Then the left pin is the emitter. So now that's at the top because we turned it to the left. Middle pin is the base, and right pin is the collector, but again we turned it to the left, so now the right pin is down at the bottom. That's going to ground right there. We got the LED. Make sure you put the LED in the right way. As a reminder, short lead cathode, long lead anode, and the current limiting resistor. So LED is going to drop about 1.5 to 2 volts, depending how much current is going through it. At 20 milliamps, probably about 2.2 volts. But you say about 2 volts there. That puts 3 volts across the 220 ohm resistor, which will ultimately set the current going through the load there. So even though the LED is dropping about 2 volts, the transistor might be dropping about 10 volts. What the voltage you got across the resistor right there will be what sets the current. Since we're setting 5 volts at this point, that will drop about 2. So we'll always have about 3 volts there across the resistor. So current's going to be the same no matter how much we raise the voltage. That's one reason why you would set up an emitter follower. You can set a current in that way. Although this circuit, we're mostly just want to make sure we got 5 volts at that point. That's the main goal. So it's an emitter follower, or kind of a voltage regulator circuit. So now we will look at the power supply. It is 7 volts right there, which is probably about the minimum voltage we want to use. Since we have a zener diode, that's 5.6 volts, and we go there. We need the supply voltage to be higher than the zener voltage by a little bit. So setting the meter to V for voltage, I don't have to move the red probe for anything than high current with this meter. I leave the red probe where it is. Other meters, you may need to move one probe, and some cases maybe even both probes, depending on the particular meter, however they have it set up. So first off, let's look at the zener voltage, see what we are actually working with. I have not measured this yet. So there you can see a little bit shy of 5.6 volts. But again, we're using a low current. We have this 10K resistor there. If we had like a 2.2K or something, which we could still use in this circuit, going to 15 volts, I believe, it'd probably be a little bit above 5.6. But there you can see we're in the range of 5.6. But it's good to know that exact voltage when it comes to checking the voltage. So we're going to go across the load now. So emitter there, and then to positive supply. Again, we're measuring the opposite way that we were with the NPN in relationship to ground. Now it's in relationship to the positive supply right there. So there you can see a little bit less than 5 volts, but we're getting a little less than 5.6 volts right there. If we go to the, we're going to put the red probe up there now, and you can see there we have, almost a 0.7 volt difference, which we expect. Somewhere between 0.6 and 0.7 is standard. So that's actually not bad right there. So that will be the total voltage difference there. Should be about 5.6, going through the load and then the emitter to base. So those voltages are basically equaling up right there. It might be like slightly different. Now you can also go from ground. So a lot of times you'll hear the NPN bipolar junction transistor emitter is 0.6 volts higher than the base. So that's in relationship to ground right now. So it's very important you're aware of which direction you're looking at. So we got about 1.4. So I'm guessing we'll have basically 2 volts at the emitter, give or take a little bit right there. And that's right, it was about 0.7 volt difference there. So yeah, 2.1 volts makes perfect sense. We did that with 7 volts. Now let's, I almost ended it there. Let's go up to 15. That's important that we do that as well. So we measured the voltages, we saw them transfer, and main thing is we should still have the voltage across the zener diode there, and actually it didn't go up as much as I thought it would. And again, now we're going to go across the load. So that's the thing, this does not depend on supply voltage. There you can see that looks way too low right there because I didn't have a good connection. I was messing something up. There we go. We still have about 5 volts across there. And again, it'll be Now there'll be a lot more difference on this side right here. This was where the difference was, and in relationship to ground. But the load is coming from the positive supply, so is our zener voltage there. So the zener is holding the voltage across the load steadily. It's the load across the transistor, which we are actually just measuring right there. 10 volts, as I said before. If we got 5 volts across the load, and we're using a 10 volt or 15 volt power supply, then we will have 10 volts across the transistor. Now current will change a little bit. It's not really changing through the load, maybe a speck. This probably wouldn't register unless it was already right on the edge of changing. But we do have some current going through that 10K resistor as well. And so it will change a little bit more than you might expect. Let's go to 17. So in any case, yeah, that's about it. Always make sure you turn off the multimeter when you're done. If there's like a power button and you have it set to measure current, get it off of measuring current. Set it to a voltage setting. But in this case, we aren't measuring anything. Once we're off, we turn it on to whatever setting we want. So it's pretty safe with this one. Just turn it off when you're done. Thanks for watching. Make sure you check out one of the other videos I'm posting on screen, and check out the links down below. They all help out a lot. I'll see you in the next video.